Hey guys, Ms. Peterson here, and welcome to AP Physics 2, Lecture 7-3, all about nuclear physics. So in this lecture, we're going to be discussing the famous equation E equals mc squared, a bunch of different nuclear reactions from fission and fusion and decay reactions, and talk about half-life. So let's go ahead and get into it. Okay, quick review. When we talk about nuclear stuff, we are going to be talking about things that go on in the nucleus, which is where the protons and neutrons are. Okay? The electrons are surrounded in a probability cloud of those quantized energy levels. Okay? And we will typically be working with isotopes. Okay? So atoms with the same number of protons but different numbers of neutrons. Okay? Now, this means that when we do the masses, we're not typically going to use the masses from the periodic table. The mass on the periodic table is the average atomic mass, okay? Because, for example, in a sample of carbon, you'll have some carbon with a mass of 12, some carbon with a mass of 13, some carbon with a mass of 14. It's all carbon because it all has 6 protons. And in a general sample of carbon, 98% of it is going to be C12, 1% of it's carbon-13, and we only use trace amounts of it for carbon-14. That's the one we use for carbon dating. So when we do these types of problems, we will need specific, very specific, very detailed masses, okay, with a lot of level of precisions. Okay. Now, what was happening was we were looking at nuclear processes, and we had our two laws, the conservation of mass and the conservation of energy. And once we were able to have technology that could measure our masses really precisely, we were seeing that the masses of our products in these nuclear reactions were slightly less than expected. Okay? We weren't getting a complete conservation of mass. And thus, the conservation of mass was replaced with the conservation of mass energy, where E equals mc squared. Okay, in a process, some mass might get converted to energy. There is energy contained in that mass. So if we lose that mass, we get the energy. So we have energy equals mass times c being the speed of light, which is 3.00 times 10 to the 8th meters per second squared. Okay. Now, also, typically when we do these units, we might be working in AMU, but on the equation sheet, it's actually just written as U. So 1 U is 1.66 times 10 to the negative 27 kilograms, which when we're working in electron volts, so with really, really small amounts of energies, we can actually just use a direct conversion of 931 mega electron volts per c squared. So note this 931 mega electron volts, that is energy. Okay, these are conversion factors. Okay, so yeah, we can convert it to kilograms, but now this is also giving us the conversion to convert it to energy. So if we're just looking for the energy in electron volts, we can just times it by 931 mega electron volts per c squared. The c squareds cancel out, and we just get that energy conversion. Okay. So the best example of this happening is in the sun. Okay. In the sun, there is a proton-proton chain reaction, and the general reaction is that we have 4 protons. A proton is typically written as just a hydrogen atom because it's just, if we have a hydrogen with a mass of 1, okay, that is just a proton. Okay, so label that, aka proton. Okay, and then it is going to turn into an alpha particle, which is a 4-2 helium. Okay. So here we can see that 4 times 1, that conservation of nucleon number, but we're not quite getting that conservation of of protons. Okay, we got 4 protons, and it only turned, by the end, there's only 2 protons. 2 of those protons turn into neutrons. Okay, and we can also see that in this reaction in these 2 E positives that are released. Those are the positrons. Okay, so plus those would be a 2, 1, 0. Sometimes you'll see it as a B positive. They did it as an E positive. So I will do it there. Okay. So that is a positron. Okay. And this one is that alpha particle. And so we're going to find the mass deficit in this reaction. Okay. Knowing that the mass of the alpha particle, okay, the 4,2 is 4.0015 AMU, or U, and then the mass of the neutrino and the positron, we're going to ignore the mass of the positron for now, is negligible. Okay. So we're going to find the mass deficit, the mass lost in this fusion reaction. Okay, so for the mass deficit, I normally do it as a change in mass. And in this case, it'll always be reactants minus products because you want to know the lost mass. If you do products minus reactants, you just get a negative number, which I guess makes sense because you do lost mass. So yeah, let's do it that way. Okay, so we have that mass will be the mass of the helium nucleus minus 4 times the mass of the proton, aka that 1,1 hydrogen. So the mass of the helium, they told us, is 4.0015 AMU. I'm going to convert that to kilograms because on our equation sheet, we only have the mass of a proton in kilograms. Okay, so let's go ahead and convert this number. I'm going to times it by 1.66 times 10 to the negative 27. And that gives us the mass of 4.0015 times 1.67, 67, not 66. Okay, 1.67 times 10 to the negative 27. So that tells us that the mass of that helium is 6. Okay, we had 5 sig figs there, so I'm going to keep that precision level. The precision level is going to be really important in these types of problems to keep it significant. You're going to need more decimals than you expect because the lost mass is so small compared to the actual masses. So 6.6825 times 10 to the negative 27 kilograms minus 4 times the mass of 1 proton, 1.67. times 10 to the negative 27. So with that, we get a mass deficit of minus 4 times 1.67 times 10 to the negative 27. A mass deficit of 2.505 times 10 to the negative 30th kilograms. Okay, that is the mass that turns into the binding energy of that alpha particle. Okay, so, and is the energy of the released photons and neutrinos in that reaction. Okay, so some of it goes into binding energy. We typically do that when we do have like protons coming together to form something, and that lost mass. So then E equals mc squared. This is the mass that turned into energy. Since we have it in kilograms, we'll keep it there with 2.505 times 10 to the negative 30th kilograms times the speed of light squared gives us 2.25 times 10 to the negative 13 joules. And there we'll have a lower precision because we only had our speed of light to 2 digits there, 3.00, as it is on our reference sheet. Yep. So That's how we use E equals mc squared. Let's do another example. We have a proton with its mass and a neutron with its mass combined to form a deuterium. Okay, the mass of the deuterium is that much. What is the mass deficit? Well, let's go ahead and find it. Okay, so this time we're going to go ahead and work in electron volts and U. Okay, this should just say U rather than AMU. It's stuck in AMU because that's what we used in AP chemistry. But our equation sheet uses U for unified atomic mass unit. So that mass deficit will be the mass of the deuterium, 2.01356, mass of the deuterium, minus the mass of the proton, plus the mass of the neutron, so minus the particles that combined to form it. Okay, and they're giving us the units to a high level of precision. So we got 2.01356 minus 1.00728 plus 1.00867. And we get negative 2.39 times 10 to the negative 3. So 0.00239 U. It's negative because it is the lost mass. Okay, the deuterium has a mass smaller than the mass of the proton and neutron. Why? Because some of the mass of the deuterium was used to bind the atom to create that binding energy. So if we have it just in the U, instead of, we're kind of using E equals mc squared, but we're really using that 1 U is 931 mega electron volts per C squared. So when we have that energy, okay, it's just forming energy, so I don't need to keep that negative sign. It's just showing that it lost mass. Okay, 239U. Then I can just multiply it by 931 mega electron volts per C squared. Okay, and you get .23 mega electron volts. So what is the maximum amount of wavelength that could be used to photodisintegrate a deuterium atom? Okay, so if we want to photodisintegrate it, we need to provide enough energy to break it apart. So 2.23 mega electron volts. Okay, and we want to know the maximum wavelength of light. So we know the energy of light is HF, which we typically rewrite as HC over lambda. Okay, and do I have it? Nope, I have it in electron volts, but not in mega electron volts. So I will have to convert there. But we can get our wavelength from HC, which is 1.24 times 10 to the third electron volts per nanometer, or electron volt nanometers, divided by 2.23. Mega is times 10 to the sixth, so times 10 to the sixth electron volts. So when we do that, we get, let me move that over real quick. Yep, and we get 5.56 times 10 to the negative fourth nanometers which would be, let's see, let's convert it from nano to milli. We know 10 to the negative 9 nanometers is 10 to the negative 3 millimeters. Okay, do we want to go milli or micro? It's negative 4. I think I'm going to go milli. Yeah, let's go milli. So that, and then, do I really need to do this in my calculator? Probably not. But sometimes I get a little mixed up, so I like to. Yep, we get 556 millimeters, which is what I expected. Okay, going up by an order of 6, so move that over there. Okay, cool. Okay, cool. Let's go ahead and look at some different nuclear reaction types. Okay, so there are a couple different types of decay reactions that you're gonna see. These are not the only nuclear decay reactions that exist. This is just some of the more common ones. Okay, alpha decay is when something emits an alpha particle. So that alpha particle is the 4,2 helium. Okay, that is the alpha particle. And then we go by conservation of nucleon number. So 86, and then I have 2 there. So that means I'll have 84 left. 222, 4 there. That means that there will be 118 left. 118 plus 4. 218 plus 4 is 222. And then 84 plus 2 is 86. And then number 84 on the periodic table. Got a periodic table here. Gonna look at who number 84 is. That is polonium. Okay. Now, for beta decay, it's when the nucleus emits either a positron or an electron. Basically, when a neutron changes to a proton or a proton changes to a neutron. And there's 2 different ways that you might see the positron and the electron represented. Okay, you might see it as a 0, 1, be positive. Okay, that's for the positron. Or the same thing, but with an E for an electron. Because the electron is typically drawn like that. Okay, but again, every now and then you'll see the beta instead of the E for electron. So carbon-14 is an example of this. So when carbon-14 decays, a neutron actually changes into a proton, causing the carbon atom to become a nitrogen atom. And it does this by releasing a electron. Okay. If a neutron that is neutral wants to become a proton, which is positive, it needs to lose its negative charge. And of course, I did it as a beta particle instead of as an electron. Okay. Now, fluorine actually does the opposite. Okay. Fluorine is one that where a neutron changes to a proton. So we'll have the 816, number 8 is oxygen, and the positron. Okay. So those are the 2 types of beta decay. Okay, we have a neutron changing to a proton by releasing an electron. And here we have a proton changing to a neutron by releasing a positron. Okay. Positrons have the same mass as an electron, but an opposite charge. They are the antiparticle of an electron. Okay. Now, often you'll see gamma decay with other decay types. This is where it releases an alpha ray when it decays. So, for example, carbon undergoes alpha decay. So it does produce the alpha particle and leave behind the 1838 argon. And then you'll just see it like this. It doesn't really have any mass, but that is just a gamma ray. And it doesn't even necessarily have to be a gamma ray. Really, it's just a photon. Okay. It is the energy that is released. Okay. One other type you might see is neutron decay. And every time you might also see neutron capture. Okay. This particle right here is the neutron. And so conservation of mass, we have 4 and 0. We need a 4 there. 13 and 1. We need a 12 there. And number 4 is still beryllium. Okay. So that beryllium just lost a neutron. Now, for the 3 main types of decay, alpha, beta, and gamma, sometimes you'll hear them talk about how penetrating they are. Okay? I know, fun. So alpha particles, because they're so big, they are slow, and they don't travel very far before they themselves tend to decay. And they can be stopped by things like a piece of paper or your skin, where beta particles tend to travel a little bit farther, but they are still stopped by things like a sheet of aluminum, where gamma rays can't be stopped except for by like a wall of lead. And that is why when you go to get an x-ray or something like that, the doctor who is exposed to those all day, every day, has to go behind that wall of lead or a metal wall in order to protect themselves from that radiation. Okay, cool. So some other nuclear reactions that we can do. This is fission, when a heavy nucleus splits into 2 smaller chunks. Okay, typically releasing energy. This is what we use in nuclear reactors. That should say reactors. Reactors. Okay, so let's see. We got 94, 40, and 54, so that's good. It's going to be a 0 there. 239 and 1, that's 240. 100 and 134, 137 is 237, so we need a 2 there, which must mean, 2, massive 2, but no positive charge. The way that probably is it is going to be 2 neutrons, 3 neutrons, 2 neutrons. 100 and 137, 143 neutrons, okay? There's a release of 3 neutrons. Okay. Oh, a neutron just has a 1, 0. There's also fission reactions. This is where 2 light nuclei combine to make a heavier one. This is what powers the sun, okay? Often produces lots of energy. They said 18.3 mega electron volts in that last step. We can also have just random reactions that they'll present you with, and we just need to use our conservation laws. So we got 8 and 1. Okay, 8 and 1 is 9, so that means we need a 2 there. 17 and 1 is 18, so we need a 4 there, so that must be an alpha particle. Slam it into a nitrogen to produce an oxygen atom and a proton, it looks like. Okay, cool? Okay, cool. Now, one of the other ones that you will see is annihilation reactions. In annihilation reactions, they're often between matter and antimatter, like a positron and electron, or they'll just tell you 2 particles combine and annihilate each other. In this sort of scenario, all of the mass is converted to energy. So positron, they each have a mass equal to that electron, so 2 times the mass of electron equals c squared, and it'll travel away as light, okay, or a photon. So we can calculate the frequency of that photon by the energy of that annihilation reaction. Okay, cool? Okay, cool. So let's go ahead and do a couple practice problems. Okay, here you're going to use conservation of nucleon number to fill it out. So we got 74 and 2. That's 2. And 72. And 180 and 4. So we have 180 there. Number 72 on the periodic table is hafnium. Okay. Go ahead and try the other 3. And then check your answers against mine. Did you get them right? Good. We have 2 examples of alpha decay and 2 examples of beta decay. And note, it's fine whether you used an E or a B in that notation. Okay. So in our nuclear reactions, again, that conservation of mass and conservation of energy is replaced with conservation of mass energy. The other true thing will be a conservation of momentum. Okay, momentum will be conserved in any nuclear reaction, and conservation of charge. Okay. Also, we typically consider these to be elastic collisions, unless it says otherwise. So often in those you will get conservation of kinetic energy. Okay. And not potential energy, because there's that nuclear strong force binding stuff and doing stuff and all sorts of things. And again, for solving them, we do them based on nucleon number. Okay. So one other way you'll see these types of problems is through these types of reactions. Okay, we got a photon colliding with an electron. So an interaction between light, a massless particle, and an electron, a particle that does have mass. So let's go ahead and find the energy of that incident photon. We got E equals HF, but they're giving us its wavelength, so we're going to do HC over lambda. So let's go ahead and find it in joules, or in meters. Yep, we have the wavelength in meters, so we need our Planck's constant HC in meters, which is 1.99 times 10 to the negative 25th joule meters divided by 1.8 times 10 to the negative 11 meters. Meters and meters cancel out, and we get 1.99 times 10 to the negative 25th divided by 1.8, 10 to the negative 11. 1.1 times 10 to the negative 14 joules of energy. Okay. So what is the magnitude of its momentum? Okay. So it is a photon. It has a wavelength, and we relate wavelength to momentum by the de Broglie wavelength. So the de Broglie wavelength of anything equals h over p. Okay. So the momentum then is h over wavelength. So we have h, which is 3.68. No, h, which is 6.63. Times 10 to the negative 34 joule seconds. And then we're going to divide that by its wavelength, 1.8 times 10 to the negative 11 meters. And so we get its momentum of 3.68 times 10 to the negative 26 kilogram meters per second. Okay. So let's go ahead. We can look at those units real quick just to show you how those work out. Okay, we got joules times seconds over meters. So remember, joule is energy. I always think of it as mv squared. So a joule is a kilogram meters squared per second squared times seconds divided by meters. Seconds and seconds cancel out. Meters cancels out with that squared. And yes, we are left with kilogram meters per second, which we know is the unit for momentum. Yep. So will the photon's wavelength increase or decrease as a result of this interaction? Okay, so these kind of qualitative questions are how the AP Physics 2 curriculum tends to address these. Okay, now wavelength. Okay, so if we're thinking about its wavelength, what will happen to its momentum? Well, initially, the photon had some momentum, but the momentum of the electron equals 0. Okay, momentum of the photon. Okay, after, the electron does have some momentum. So the momentum, I will just call this initial and final. Okay, initial, so the final momentum will be less than its initial momentum. Okay, and if your momentum goes down, your wavelength increases. Okay, it will increase. Okay, the photon, another way you can think about it is the photon loses energy. And since E equals hc over lambda, lower energy, higher wavelength. We know that. Okay, cool? Okay, cool. Now, I did want to show you guys the actual mathematics of this in case you're interested. This is something called Compton scattering. Comes up a lot in these types of problems, but actually isn't in the AP Physics 2 curriculum. So you don't really need to worry about these equations, but you can kind of see how that photon is the energy divided by c. This comes from E equals mc squared, okay? And then we know speed, c is just a speed, and momentum is mass times velocity. So you can think of energy as that momentum times c. Okay, that's where that part of the equation comes from. And then we have hc over lambda, hv over c. And in here, that is f. Okay, it should be frequency. That is what that's representing. And f over c equals that wavelength. Well, the inverse of the wavelength. Okay. And we could find the momentum of the electron and the momentum of the photon in those reactions. Okay, cool? Okay, cool. Oh, and remember it's conservation of momentum. Conservation of momentum. So let's get into half-life. Okay, half-life is the time it takes for half of the radioactive atoms to decay. So if something has a short half-life, it takes a really long time to decay. Short half-life, you're going to get lots of radiation in the short term, which is really good for when they want to track how something's moving through the body or something like that. Now, important to note, this does not depend on environmental conditions, okay? The nucleus of an atom doesn't care if it's raining outside. It's not going to make it decay faster like a human body would or something like that. That was a little morbid, sorry. I don't know why my brain jumped to that. But yeah, okay, nucleuses don't matter about environmental conditions in their decay. And the actual equation for nuclear decay or half-life isn't on the equation sheet. I'm going to show you guys how to solve the problems without the equation using what I like to call the table method. But if you know the equation, you'd rather just have the equation. It is that the amount remaining in whatever units you're doing will equal A, not the initial amount, times 1/2, because, you know, it's a half-life, to the power of however many half-lives you've had, which is typically written as T over tau, where tau is the half-life, okay? And T, of course, is the time. So at 0, you're at that full. After 1 half-life, okay, so 1 tau, you're down to half of what you had. 2 half-lives, a fourth, 3 half-lives, an eighth, 4 half-lives, a 16th, etc., etc. Okay. Now, some common radioisotopes that we use are heavy hydrogen, aka deuterium. We use that for amino acid labeling and when we're analyzing cells and stuff. The protein labeling of the I-25 is a really cool one. They actually inject it into the bloodstream with a medication. And then by tracking where that radiation is coming off in the body, they can track the flow of that medication through your bloodstream, which I think is pretty cool. Yeah. So let's go ahead and see how we can answer these two questions. Again, I'm going to show you guys how to do this without the equation, but if you want to use the equation, you totally can. Okay. I do it using what I like to call the table method. So in the table method, what we have is we're going to have number of half-lives, time, and amount. Okay. And the amount can be in whatever units that we're talking about. Okay, we're looking for percentages, so my amount is going to be a percentage. So, you know, after 0 half-lives, you have 100%. And then after 1 half-life, which is 57,000 years, you will be down to 50%. After 2 half-lives, which is 57 times 2, 11400, you are down to 25%, and it's not really asking us the time. It just says after 5 half-lives, so we don't really even need to worry about this. After 3 half-lives, we'll be down to 12.5%. After 4 half-lives, 6.25%. After 5 half-lives, 3.25125%. Okay, so approximately 3.1212%. Okay, cool. Okay, cool. Now, I want you to see if you can figure out how to set up this problem. Okay, and see if you can figure out how to solve it out. And I will show you both methods of solving it. Okay, so first method, the one that I like to use, is the half-life. Okay, I have all the information that I need on sample 1. So I'm going to do number of half-lives, okay, and then time, and then mass for sample 1. Okay, so let's go ahead and see. For sample 1, after 0 half-lives, you know, at 0 time, you're at 52 grams. 1 half-life is 3 days, and you will be down to 26 grams. 2 half-lives, 6 days, 13. 3 half-lives, 9 days. 13 divided by 2 is 6.5. Okay. 4 half-lives, 12 days. Ooh, look at that's what I was looking for. We are down to 3.25. And this are grams. Grams. Okay. Now it says, what is the half-life of sample 2? After 12 days, both samples have approximately the same mass remaining. So that means that for our other one, number of half-lives, that's what we don't know. Or actually, we know the time, okay? And then our mass, we know it started at time 0 and 0 half-lives at 200 grams. And then we want to know, we know that after 12 days, it got down to 3.25 grams. So how many half-lives is that? Let's go ahead and see. So I'm just going to go 150, 25. Oh, I can probably do this slightly bigger. 25, 12.5, 6.25. So that is 1, 2, 3, 4, 5, 6 half-lives. So 12 days divided by 6, it must be 2, 4, 6, 8, 10, 12 days. So the half-life is approximately 2 days for that one. Wait. 1, 2, 3, 4, 5, 6. Yes. Okay. Now, another way, if you wanted to do this using this using the equation, okay, it says that their amount remaining was the same. So if we do it based on that, okay, the equation is A equals A naught times 1/2 to the number of half-lives, or T over tau, So it says the number remaining is the same, and we have all the information for sample 1. So we would do the A1 equals A2, okay, those amounts. So for the sample 1, we would have 52 grams times 1/2 to the, T is 12 days, so 12 over 3 equals 200 grams to the 1/2 of 12 over tau. Okay, and then it just becomes a complicated algebra problem. 12 over 3 is 4. So 1/2 to the 4th, or 52 times 0.5 to the 1, or to the 4th, gives us 3.25, you know, the number of grams that we had remaining, equals, 200 grams times 1/2 to the 12 over tau. Okay, so 3.25 divided by 200 gives me 0.01625 equals 1/2 to the 12 over tau. Okay, and then let's see, how do we get this out of there? Oh, so get it out of the exponent by taking the log of both sides. Okay, so let's see, the log of 0.1625 is negative 1.789. And then when we take the log, that will pull it out in front. So we'll have 12 over tau times the log of 1/2. Okay, so the log of 1/2 is negative 3.01 times 10 to the negative 1, so negative 1.789 divided by that answer. Okay, and then 12 divided by that. And what do you know? We get tau equals 2.02. So about 2 days. Okay, cool. Okay, cool.